There's a couple of key things to focus on in section 6.9. One of them is this equation right here. We've actually seen this earlier when we were looking at section 6.6, and we saw that there was a relationship between the net force and the derivative of the momentum. Here we're actually seeing a little bit clearer. So this is just the radial component of the force. If you wanted to find, say, the x component, you just take the derivative of u with respect to x, the y component, derivative of u with respect to y. And you can see that this equation is really the same as this equation right here. Integral equations and differential equations are usually just different ways of writing the same thing. So if we take this equation right here and differentiate u with respect to r, take du dr, that's the same as taking the derivative of this integral with respect to r, f dot dr. And so what this means, and I'm kind of ignoring the vector signs here, but when you take the derivative of something where you're integrating against the same variable, the integral and the derivative just cancel out. That's why the integral is sometimes called the antiderivative. So from this equation, we see that du dr is equal to negative f sub r, or moving the minus sign over, we get this equation right here. So as I mentioned before, this is actually giving us a relationship between the potential and the force. So if we're looking at a potential versus distance graph, we can figure out what the force needs to be based on that derivative. Now, for the gravitational force, using the fact that F grav is negative g m1 m2 over r squared times r hat, and dr, the vector, is actually equal to r hat times the scalar dr. So I plug that in here. The dot product is simply going to be r hat dot r hat. And when you dot a unit vector into itself, you simply get the scalar quantity 1. So what I can do is rearrange this, and I get the two negative signs cancel. The integral of g m1 m2 over r squared times dr. And notice that g, m1, and m2 don't depend on r at all. Those are constants. And so I can pull those outside of my integral sign. So we just have the integral of dr over r squared. Now this is an integral that you should probably be fairly familiar with. And the result here is just going to be a negative g m1 m2 over r. So that's my gravitational potential energy. This is one of the key things that comes out of this section. So make sure that you're familiar with that. And one other thing I think you should do is take a look at the example on page 249. Make sure that you understand that example, that you can work through it, and you understand everything that they're doing there. If you have anything that's not clear, do feel free to come talk to me. I'd be more than happy to help where I can. One other thing I want to point out is, as a result of this minus sign, when we plot u versus r, well, this is going to look like a 1 over r graph, but because of the negative sign, it's going to be a negative 1 over r. So it looks something like that. Now remember that the force can be found from the slope of this. So this is telling us what the force is by looking at where this is the steepest, the force is largest. Where this is the shallowest, that's where we're going to have a smaller force.